Welcome. Good to see some of you. um, plan today is just to continue talking about relations, maybe a little bit lighter on the side of intensity of the math. So we can go through it slowly. But before I get started, I just want to mention a couple of things. Posted some announcements about this, but I just want to make sure everybody got the messages. One is, here's our Canvas page. I set up what I'm just going to call a study hall for the course. So this is just a Zoom room where you can go whenever you like. You don't need me to be there. In fact, I don't plan to ever really go there unless you want me to. I did set it up so that you all should be able to share screens now. But if you have any trouble getting in or working in there, just let me know. And I did see that, Brandon, you had sent out a message as well about setting stuff up. That's great. You guys are totally encouraged to collaborate as much as you like. Yeah, and so I do think that, as Brandon probably can attest to, like, as students, you are able to set up your own, host your own Zoom rooms, right? Yeah. I think
yeah, we're verified accounts through the university, so we get all the various benefits from that.
Yeah. So just be sure that that's right. As long as you're logging in with your single sign in with your UC Denver email, that should work. But if you don't want to worry about it, there's a room here. You guys are welcome to use it as much or as little as you like. And the other announcement was, not assignments, was I just wanted you all to know about this modified pass-fail policy, the P+PF policy. The deadline for that is the 25th of October, which is Sunday. And so basically the breakdown is if you get a C- or above, that would be a P+. That can count towards any CLAS requirement, any major, minor requirement, works as a prereq. So it works just the same as if you had gotten a letter grade in the class, except it doesn't factor into your GPA. That's the only difference. If you get a D-, D+, that would give you a pass. You would get credit for the course. Does not factor into your GPA, but it can't be used as a requirement towards a requirement. And then an F is just treated the same way as if you would have gotten the letter grade. So yeah, that's one big difference. If you were familiar with how this policy worked in the spring, there was no F. Now there is a possibility for that. But if you want to make this change, it's a schedule adjustment form that you need to send to CLAS or to the registrar's office. Nobody needs to sign the form. So if you've seen the form, it might be confusing because there's a spot for the instructor's signature. There's a spot for the dean's office to sign. Neither one of us need to sign it. So I don't need to approve you. I'm not able to. You all are uniformly able to do this change. I don't even think I'll know who made that change from my end, but if you do, or you have some questions about it, or you want to let me know that you made that change, that's totally fine. And any questions about that? Okay, so let's pick up from the reading quiz that you guys took. Just to see if there were any questions on that. So we were talking about relations last time, either a relation defined on one set or a relation defined from one set to another. And so we had done the less than. This is one that we did this one together. So this top one, sorry if I'm making you dizzy. This top one was the reading quiz. First question. So here's our set, and if we put this relation R, which is defined as the less than relation, and we want to identify which of these are true, then which of these would be true statements? I think that's what the quiz was. Maybe I wrote it wrong. Does that seem familiar?
Wasn't the quiz like greater than? I don't know. It was weird because it said use the less than relation, and then it had the greater than thing.
Yeah,
Greater
I'm looking
than.
at this now thinking that this quiz question didn't make sense. Yeah, so I might have to
I
adjust.
think it was like X was less than Y.
It was X. It said X was greater than Y, and it had but it had R as less than relation in the question.
Yeah, let me take a look. That doesn't sound.
Because I remember the answers were 3R1, 5R, or not 5R2 because 2 is non-relation.
Oh, I
and then
defined this as the less than relation, but then the next line I wrote it as the greater
than. Yeah,
relation.
that's why I was a
Okay.
little confused, but it ended up being greater than.
Okay, I'll make sure everybody gets credit for that one. Sorry. So it's good that we're talking about this now. So let's do it the way I intended to ask it, not the way I actually asked it. So we want to make this the greater than relation. Okay, and so what that means here is that we would say X is related to Y as long as X is greater than Y. Okay, and there's a condition here that this is a relation on the set A. So we're only considering things that are in A. So we need to check that these things are in A, and then we need to check that it satisfies that relation. So out of all of these relations, do any of them kind of violate that condition?
Yes.
Which one?
5R2.
That's right.
How do you say that? Is it 5 relation 2 or is it just 5R2? Or is it...
You can say it either way. Yeah, you
Okay.
can say 5R2. Yep.
Okay.
Yeah, so there's a 2 here, but that's not in there. So this relation over here, that's not true. Even though 5 is greater than 2, 2 is not in A. So there could be a relation.
For 7R7, because there's only one 7.
So that's okay, because you can define a relation on itself. So this relation is really a map. It's a subset of A cross A. So this is not a true statement here because 7 is not greater than 7, but if it was a greater than or equal to relation, then that would be fine. But this doesn't pass muster here because of the fact that they're equal and they don't, the first one is not bigger than the second one. So that's basically all we're looking at, right? We want to make sure both of the numbers are in the set and the first one should be bigger than the second one. So 3R1, is that one okay? You can give me an up or a down. That's fine. 3 and 1 are both in here, and 3 is indeed bigger than 1. 7, not related to 9. Is that true or false? That is also true. That's right. Since 7 is less than 9. So that is, in fact, true that this does not satisfy that relation. 3 related to 9. Nope. Okay, because 3 is less than 9. That's right. So for this one, there should have been 2 correct answers. Sorry about that. Any questions? Okay, and then for the second question was this set A. Now we define this relation R, which is saying 2 things are going to be related if the first one divides the second one. That's the relation here. So then we would look at these and say, remember, we want to make sure, first of all, that these values are in our set, and then it satisfies this relation. So which of these can we rule out because we've got a value which is not in our set A?
2R10.
Yeah, so yeah, 2 does divide 10, but 10 is not in our set. So that can't be a relation. And then we look at the other. So does 2 divide 6? Does. Let's check. Is 5 not divide 8? Does not divide 8. So that is also a true statement. 4 divides 8. That's a true statement. 6 does not divide 3. So that one's wrong. So it has it in, if we flip the order around, then it would be fine. So these are examples of how we can define a relation on one set. And we did take a look at some examples where we can define a relation from set A to set B. So there's a relation that's called the total relation of a set or between two sets, which is the set consisting of all possible relations. So you don't want to do this for large sets, but just to illustrate what this would look like with reasonable sets. So if I had a 1, 2, and a 3, 4, the total relation would be all ways that I compare 1 with everything in B, every way that I compare 2 with everything in B, and so on. Any questions? Okay, and then there's the kind of least interesting relation, which is the empty relation, which just means nothing in A is related to anything in A, or nothing in A is related to B. So that would just consist of no relations, which is the empty set. Okay. Any questions, thoughts?
Why was it E is equal to the empty set? Why did we use E?
You can call the relation whatever you like. So
Okay.
sometimes we use a letter which is descriptive of the relation that it's representing is all.
Okay.
So like in absence of anything, R is the generic term, but sometimes you might use a letter which is actually describing the relation.
Okay. Is that what you use T too? Yeah.
That's right. That's why I
Yeah,
used T up
T.
there. Yep.
Sounds good.
Yeah, and what's important in that these relations are sets that are defined as a Cartesian product. Either if we're talking about a map from A to B, it would look like that. If we're talking about a relation on a set itself, then it would look like that. And so this is just saying this relation set doesn't contain any relation, so we got an empty set. Okay, so yes, so oftentimes we describe relations with some rule or a formula or something like that. So here are some examples of relations. These don't just have to be defined on numbers. So we could take the set of all students at CU Denver, the set of all courses at CU Denver, and then define this relation between if a student is in a certain course, then we would say they're related. So for example, just because you're first in my like Brady Bunch grid over here, we could say that Dylan is related to Math 3000, for example. Yeah, so here were these total and empty relations that we talked about on the previous one. Sometimes it's just easier to use a concrete example to illustrate them. And here's kind of a topological relation that we can define. So you'll see some of these things when you start to move into real analysis. And so this is what's called like the epsilon nearness relation. And what this is saying is we've got some point, X, Y, and then we're gonna kind of consider what are all of the points. Oh, sorry, that's not what's going on. X and Y are both real numbers. Yeah, so we're not in R2, sorry. I went one dimension too high. We're in one dimension. So we might have a value X, and we could define some epsilon. And then we're going to say all of the values that are within epsilon of X are going to be related to X. So all of these values Y would satisfy that, but if we pick some value out here, then we would say X is not related to that value. Okay, so let's try some polling questions here. And so here are some relations that I'd like us to consider whether or not these statements are true or false. So here we're going to define P as a relation on Z itself. So P is going to be some subset of Z cross Z. We're going to define this as the empty relation. I think I've got, yeah, let me open this up. So that's something to consider. I think I've got this quiz so that they're all going to be asked at once. Over here, we're going to define the total relation on R. And then over here, we're going to define this nearness relation on the real numbers, where we're going to pick an epsilon value of 0.01. So if it helps, you know, the first one is our pi, and then we're going to kind of consider right, whether the second value is within 0.01 of pi. So all of these values in here would be related to pi. All of these values that are outside would not. Okay, so I'm going to open up this poll for all three of these. I think two of them should be pretty quick. The last one, you might need to do some calculations on that one. But once you've got them, please just submit them in. And if you've got any questions, you can chat them in to me. Okay, so let's take a look at the results. So the first one was asking here, you guys can see the results, right? This is what I don't know about on your own. Yeah, okay.
Yeah, we can see it.
Yeah, so for for one, we're looking at the empty relation on integers. Is one related to one? Definitely not, because there's no relations in the empty relation. So one related to one, although it is like a very trivial thing, that is actually a non-empty element of that set. So if the question ever goes like this, and you're asked is something true or false, then no matter what two things you pair up, it's going to be that is not true. And you know, if I said this, that would be a true statement, right? Because nothing is related to anything else. Okay, so any questions about that? Okay, then in 2, so that was looking at this relation, the total relation, and it's kind of the total opposite here, right? In that, like, as long as both of these things are real numbers, then it's fine. If I had a complex number there, that would be a problem because that's not in our set. But this is going to be true for 3 related to 3 related to 7 is true, and 7 is related to 3. So for those that were not sure about these, feel free to ask or chat in if it's not clear how we're getting these, how we're gauging the trueness or falseness of these. Okay, so those were both true. And then this last one requires a little bit of calculation here. Most people that responded said it was true and some weren't sure. So this is true. And for someone that said, I definitely think it's true, you want to, or I think it's true, walk me through how you decided it was true?
I just divided 22 by 7 and then subtracted pi from it and compared whether that value was greater or less than 0.01.
Yeah, and so what do you get?
The difference is 0.00126.
And that is indeed less than our epsilon value It's that. So this one is true. That's right. Okay, so I think like thinking about these relations might not be what's kind of tricky about this, but maybe the notation and how we express this is a bit different. Any questions? Okay, so I'm gonna just break this up into breakout rooms here, since I'll be curious to see different relations that people might come up with on these sets. So question 4 is saying, okay, E is going to be the set of all words in the English language. Let's come up with 3 different relations on E. And so when I say 3 different relations, I'm like trying to describe them in words as opposed to like writing them out as sets. So just say, this word is going to be related to that word if whatever the case might be true. And then in this one, in 5, we're going to take all the people on Earth. We're going to take all of the women on Earth, and S is going to be this relation. We're going to say X is a sister of Y. And so the question here is, I see. So yeah, so this is kind of saying we can define this relation on either of these sets. So we can define this relation S there are kind of 4 different sets that we can define this relation on. I could define this kind of sister relation on the set P itself, from P to W, from W to P, and from W to itself. Okay, and so, yeah, I'll just kind of leave that somewhat open-ended to just kind of think about how this relation would work on these different collections of sets. So when you're kind of thinking about 4, I have changed my settings, I believe, so that when you go into breakout rooms, you should be able to share screens. Might be nice just to get a whiteboard up and just type away. That will help when Nat and I pop in to see what you guys are discussing. But any questions before we break you up? Okay, hello, everybody.
Howdy.
So yeah, I'm just kind of curious, we can just type them up here. So on question 4, if you want to type in 1 or 2 relations that you came up with, that'd be great. I'm just kind of curious what the groups came up with. And hopefully we don't start typing on top of each other. But I think that you can type on this. Is that right or no?
Can you see what I put there, or do I have to click off of it?
I think you need to click off of it. Yeah, there you go. Perfect. Yeah, so while you're typing, I don't see it, but once you finish typing, it appears. Or
Yeah,
chat them in if you prefer. But I'd like to have them so that we can all kind of look at what each other came up with.
We were having a massive debate as to whether you could take a set of individual items, in this case words, and create a subset of multiple items in each entry, in this case like a sentence.
Our argument was over the fact that we could make a relation. The relation was like, if you said our relation is the set of sentences, you can't take words into sentences. Yeah.
Okay. We can debate this in a sec, but I would like to see, and this is a really good thing that came up, but can people please chat in more? Yeah, so like Lindsay, Molly, Victoria, one of you can chat in something that came up. Yeah, Dylan, Heidi, Wilfred. So someone from each group or multiple people, just type it in over here. We won't see who enters what, so there's going to be some anonymity there, so don't worry about that. And if you're not able to get the whiteboard working, then you can chat it to me. Thank you. And I can copy and paste it in, I think. Actually, I can't, but I'll transcribe. Okay, so let's take a look at some of these. So the most important thing here is this has to be a subset. I don't know how you typed in, how do you type in a subset symbol?
I have a big spreadsheet that I created from a Unicode site.
Ah, okay. Yes, so this has to be a subset. Let me call this R. This relation should be a subset of E cross E, meaning your elements in here should be word 1, comma, word 2. So keep that in mind. So we're just trying to say, here's a word, here's a single word over here. Let's come up with a way of saying that these things are related by coming up with some property that's either true or false. And I talked with some groups that had some really good ones, but there's some reticence to share them. Okay, and so, yeah, so let's think about this one. So this one came from group. And so the only question I have is, what do you mean by absolute value of a word?
So the size, so how many letters are in the word?
Yeah, okay. And so then there's all sorts of ways that you can define relations by counting letters of a word. Yep, so totally saying like two words are related if they have the same, if the first one has less letters than the second one. Not less words, less letters. Okay, and that's either true or false, right? There's no gray area with that property. Sorry, I forgot you don't see it until I hit enter.
Actually, we can see it as you type it.
Oh, I'm special. Great.
Yeah.
I have the power. Yeah, so let's take a look at these other ones. So X and Y both start with A. What does the group think? Does that seem like a good relation on this set?
I'd say it's a valid relation, yeah.
Yeah, I mean, and really the only thing you want to think about is if I have two words like this, then you want to just think about, oh, cool. You know, is this property that we're defining it, is it have to be true or false? And it does, right? Either they both start with A or they don't. So that one works out. So someone want to explain the relation here of words with two O's?
Yeah, I put that one. So I was just thinking like if a word has two O's, if the other word doesn't have two O's, then they're not related.
Okay, so I think that's a little bit different what you described in words with, no pun intended, with what you've written over here. So and this came up with some other groups as well, and that you just want to be careful that we're not just defining a subset. So like just to take this example above where we're saying X and Y both start with A, that's a totally valid relation. But if I just say, this is a subset, right? Sorry, I don't know. That is a subset over there, as opposed to a relation, because it would just consist of, you know, any word that has an A in it, but it's not saying, how can I decide whether this thing is related to that thing? And so you just want to be sure that when you define this, you're defining how are two things going to be connected to each other. So do you want to just say that again, Wilfred, and we can see if we can write that out in a way that it clearly is a relation.
So I guess you just say R is X and Y both have two O's.
And so according to this, for example, we could say 2 is related to boot. They both have two O's, but 2 is not related to boat. Is there a shortcut for not R? We could say that 2 is not related to boat because boat just has one O in it. And that's a distinction, right? So one of them is defining how we're going to pair two things, whereas the other is just picking a subset out of E. So does that distinction make sense?
Yeah, thank you.
Yeah. Thanks for responding. Yes. Okay. Okay, so now so this one that says R is a relation if we have a grammatically valid sentence. That's more like defining a subset on the set of all sentences, right? And so we could have the set of all sentences. Some of them are not actually sentences. They might not have a verb in it or whatever the case might be. And then we can say, okay, all of the ones that actually are grammatically valid are going to be in my set. So that would kind of just more be like a subset of the set of all sentences. So in purple over here, we've got yeah, so you could say that two words are related if they can form a grammatically valid sentence together. Probably that's almost every pair of words if people can get really creative with how you can phrase sentences. But yeah, that would be a way to refine the first one. Yep. And so for this one down here, someone want to just explain what you meant by this one?
That was part of the let R be a grammatically valid sentence above it, just as an example of the thought process behind it. But you explained it, yeah.
Yeah, so you could say these two words are going to be paired if they can form a two-word sentence. That would be less relations. That's right. Yeah. Okay, so are there any other comments about that? Okay, then the next part was talking about this. I'm going to clear all this. Does anyone want to have this for some reason? Well, okay. So now we were thinking about P was the set of all people in the world. And we're going to say W something like this. Okay, so we've got a set of all people, set of women in the world, and now we're going to define S as a sister relation in the sense that we say X is related to Y if X is Y's sister. First comes the sister, then comes the other sibling. And so this was kind of open-ended, but I was just thinking, we can think about this as mapping from P to W, from P to P, from W to itself, and from which one didn't we do? W to P. And maybe the question that we might think about is, which of these relation sets would contain the most pairs of matches, and which might contain the least pairs of matching? So anyone have any thoughts about which of these relation sets might have the largest collection of ordered pairs that would satisfy that relation?
P to P.
Okay, so those are the two biggest sets, right? So that's a pretty good assumption there, that the larger the sets are, the more inclusive they are. So W here is a subset of P. That's certainly true here. So yeah, this is going to be large. Oh, I just circled the wrong thing. So this one is going to be large over here because, yes, P and P are quite big. Are any of these other sets going to actually be the same size as that one? Any of these other relations?
P to W and W to P would be the same size.
P to W and W to P. So let's think about this. So if I'm going from P to W, then what do you guys think?
For the P to W, is the P the X or the W the X?
So from P to W, the first part is always going to be coming from the first set. So whatever comes first would be from this set, and whatever comes second would be from that set, for example, if we were looking at it as P to W.
So that's all the people in the world. 2 is potentially a sister of any women, whereas the other one is any women is a potential sister to anyone in the world. So it seems to me that the W to P would be the larger value, larger potential value.
So let's consider these two sets over here. For a second, and so these two sets are going to have exactly the same size, right? So if we're looking at this relation, we can rule out, right, anybody who, oh no, phew, we can rule out anybody that does not identify as a woman in set P, right? Because they're not going to be a sister of anybody. So all of the men that are in set P they're not going to be in this relation at all, right? Because they're not the sister of anybody. So whether or not the first one is P or the first one is W doesn't really affect anything, but we do get an effect with the second one, right? Because the larger we make the second set, then the more possibilities we have for matching brothers and sisters and sisters and sisters and so on. So this one down here would really just,
I don't think it's going to let you delete the pink.
I don't want to. I want more pink. Maybe that's clashes with the red there. So we'll go with blue. So this one over here, well, first of all, the W and the W, right? These are the smallest two sets. So it might make sense to think about this one as the smallest because now we've eliminated some possibilities and we're no longer thinking about who might be a sister to a brother, right? Now we're just thinking about matching two sisters to each other.
Yeah, but
thinking
with that
that-
same logic, wouldn't P to W be that same value as W to W?
That's right. These two would be the same for that reason. So whether or not the first one is P or W has no effect on the number of relations, but whether or not the second one is a P or W does have some effect on the number of relations, because that's saying whether or not we're considering only sister to sister or whether we're considering sister to brother and sister to sister. Okay, so I'll stop here for today, unless you have any questions about these. And we have a couple of extra minutes, so you know, you're welcome to enjoy that couple of extra minutes. I want to just talk about one thing, if you're curious, while we have a couple of extra minutes. There was a question on the homework assignment that you just handed in that was like this proof of all horses have the same color. And then there was some potential proof for that statement. Does that sound familiar? Let me open it up in case it doesn't. Yeah, so this question 4. And so they go through a base case and they go through an inductive step. And this one was tricky, I think, to identify what the error in logic was here. There is an error because we know that all horses are not the same color. So there must be something wrong with this proof. Did anyone catch what the issue is?
I think that proof runs into problems if you're just talking about two horses.
That's right. Yep, that's right. So the gist of the argument here, so the problem was in the inductive step. In particular, yeah, we don't handle the case 2 in between. So the proof here is saying, okay, if we have n horses, then let me take n minus 1 of them. They all have to be the same color. And now let me pick a different set of n minus 1 that contains this last horse. They all have to have the same color by induction, so therefore every horse is the same color. But if we think about how that would work when you have a case of 2 horses, right? You can say, okay, here's the gist of their proof if we had 3 horses. And so their induction works fine with 3. So they would say, okay, we're going to assume this is true for 1 less than or equal to k, which is less than 4. So maybe that includes 3. Or let me even chop that off even more. Let's just say here, we're going to assume this is true for n equals 2. And then we want to show that this is going to imply that it's true for the next one, n equals 3. And you can think about the way that I'm going to describe this is the way that it's described in the proof, where if you went from 3 to 4 or 5 to 6 or whatever, is that they would say, okay, let's take a look at these two. We assumed it's true for n equals 2, so these 2 horses have to have the same color. And now we can pick another collection of 2 horses. These 2 horses have to have the same color, so therefore all 3 of them have to have the same color. That was kind of the gist of that induction hypothesis. But if you think about how we can make this jump from n equals 1 to n equals 2, well, now I've got 2 horses. And I could say, okay, by induction, let's take a look at this one. All of the horses in this set have the same color. And now let's consider this one. All of the horses in this set have the same color, but there's no third horse which is linking these together. So the problem in that proof was kind of a subtle thing, which is the base case was n equals 1. You would need to think about n equals 2 as a special case as well before you moved into n equals 3. And there's no proof for showing that two horses have to have the same color. So that's where that proof falls apart. I don't think they went through anything else incorrectly in their proof. They just missed that one link from 2 to 3, or excuse me, from 1 to 2. Okay, so that's a wrap for today. So got homework due on Monday. If you have any questions, I've got office hours tomorrow from 10:30 to 11:30. Otherwise, I'll see you guys on Monday. Have a nice weekend.